In this video, I'd like to lay out my view of how programming relates to the fields of math, science, and engineering, and give some advice on how to become a stronger programmer by looking at that relationship. I think largely this topic generates debate that doesn't go very far. It seems to me like every iteration I've seen of is programming a field of engineering largely comes down to some philosophizing about the question and doesn't really seem to provide anything that makes me a better programmer. So I'd like to focus more on creating the framework for understanding these fields and then placing programming in and amongst them and generating programming advice from that exploration, and not so much on settling the debate of how to classify programming. It's largely irrelevant to me how it's classified, and it's much more interesting to pass on advice. For the most part, this video is targeted at programmers, but there's going to be a long section there where I'm just talking about math, science, and engineering and the philosophy of those fields. So if that's a topic you find interesting, you might find this video interesting. But by the end, I will switch to giving programming advice. So that's just sort of to give everyone an idea of how much of this video might be relevant to them. Obviously, watch as much as you find interesting, but that's just a little, idea of what to expect. And with that, let's get into it. In order to create sort of one conceptual framework that binds these fields together, I think it's useful to talk about emergent behaviors of systems. So rather than trying to define that, I think it's more useful to explain emergent behavior by examples. So I'm going to give an example of emergent behavior in the game of chess. So first of all, if you're sitting down to learn the game of chess for the first time, you might have someone there who will sort of just teach you the rules. And the rules you will learn will include things like, this is the board we play on, here are the pieces, here's how we set up the board. Here are the rules of motion that each piece follows. So, rooks move like this and so on. Of course, there's also piece interactions you learn about, how they will bump into each other on the chessboard, sort of, and how they can capture each other, how pawns can be promoted, and then you'll learn about some other special moves in the game at some point. And of course, at some point, they'll have to tell you what the victory condition is to checkmate your opponent, and then you've kind of got the rules of the game. That's the rules of the game, and you can use that to start playing. There's nothing else you need to know to play the game correctly. And you could sort of think of that set of rules that you've been taught that define the game as like the laws of physics in the universe of a game of chess, right? It's like, this is how the system evolves. There is nothing else to it. There isn't some mysteries behind why the knight is what it is. That's the way the knight moves. It doesn't move in straight lines like everything else. It moves in bends. That's just the laws of physics to a game of chess, right? So here's an interesting situation that can come up. This is called a fork. Now, the first thing that's interesting about a fork is that the word fork does not appear anywhere in that list of rules I gave you. I didn't say that the person teaching you chess has to tell you about forks for you to be able to play correctly. But what's also interesting is that if you have someone teaching you chess, after you've learned the rules, you probably will learn about forks. Forks are a really useful concept that get taught fairly early on in the process of learning to play chess better. And once you know about them, you'll think about them in a lot of different ways. They'll be a part of how you think about chess from then on. So here's a kind of interesting question that I think that brings up, which is, are forks real in the universe of chess? Is there really such a thing as a fork in the universe of the game of chess, right? And I think that the answer is that yes, forks are real. They do occur, but they aren't fundamentally real, right? Like, the fundamentally real things are pawns, bishops, knights, kings, queens, etc. The fundamentally real things are the squares and the movement rules. That's what's fundamentally real about chess. But there are all these things that are emergently real too. And so it's like a different criteria of being true or real in the universe of chess, but it's still valid. It's emergently real. Forks do exist. They just have a different criteria that they meet because we're talking about an emergent phenomenon. And that's kind of how emergent things tend to work. We're talking about something that isn't the original building blocks you had of a system, but that sort of, in the way this diagram is showing, at the bottom there are these building blocks that then a new thing emerges out of that. And the new thing is real in the emergent sense, not in the fundamental sense. And anytime we see this pattern, we're going to call it emergent. So we have some building blocks that don't initially have a particular property or a particular shape or a particular structure or rule or whatever, but then a thing emerges out of those building blocks that does have some new property that wasn't a property of any of the things in the initial rule book. That's what we'll be calling emergent behavior, and we're going to use that to understand how these different fields operate. So what is science? In particular, what counts as science and what doesn't count as science? How does the process work? What does it do for us? Why do we bother to do it? So I think the easiest way to define science is to start by looking at the kind of problem that we face when we don't have science, and then explain science as sort of the best thing we've got so far, trying to solve that problem. So the kind of problem science is trying to solve starts with the fact that we have access to a lot of information through our senses as humans, right? We can see all kinds of colors and light and darkness and try to explain that. We hear different pitches and volumes and we want to explain that. We can see things moving, we can see things falling, and we want to explain why things behave the way they do mechanically, and so on and so on. I could go on listing things we can observe. And we have a natural inclination to ask, why is it that we are observing these things? The thing we would like to have is sort of a description of the universe that we inhabit that's built out of very simple building blocks, very simple rules, sort of like in the universe of chess, how the rules of the games of chess are the fundamental laws. We'd kind of like to know what are the fundamental laws of this universe we're inhabiting. But the situation we're in that the sort of scientific method is trying to approach is that we have access to some part of the universe, but those things we have access to are generally emergent behaviors, not actually fundamentals of the laws of physics of our universe, right? We don't have direct access to whatever the fundamental rules are. That's why we don't know how everything works and why we're here. We have access to very high-level emergent behaviors that have come out of many layers of fundamental rules that then have another emergent layer on top of them that then become another layer of fundamental rules, and so on. And science is us trying to peel that back and figure out what are those underlying rules that describe or explain to us the phenomenon we're actually observing. So the scientific method is just sort of our collection of the best ways that we know of so far for us to try to answer those questions. So a few examples of things out of the scientific method and how they are helping to answer those kinds of questions. One big thing is everything in the scientific method is data and evidence supported, which means gathering data via observation and experimentation. And that's because if you try to figure out what those building blocks are by philosophy and making it up, it turns out that we have a really good creativity as humans. We can come up with good sounding explanations for things and good sounding theories of the fundamental laws of the world, but just because they sound good and seem to fit together doesn't mean they actually are the ones in action in our universe, right? So we need to gather data from our universe so that we can figure out how to rule out possibilities that we'll come up with that are just not relevant to the world we're living in. Another thing we have to do with the scientific method is account for the noise in data collection, and also the problems that come up with, like, sometimes people are going to lie and falsify their data collection or have super strong biases that they're not aware of. And so that's why we have reproducibility in science. The idea is, hey, we need to make sure that if we're going to base stuff on data, that the data we're getting is something that will reliably come back every time we try to test it, or within some kind of tolerable range of errors, we can get the same results every time. And then, of course, another part of the scientific method that I think is valuable for the purposes of this video to mention is the idea of controlling for variables and changing one variable at a time. And it can sometimes be difficult to digest this and take it seriously because it can feel like your intuition will guide you to a better guess. But often it turns out when I'm getting stuck and lost in an investigative sort of scientific mode problem, that getting a little bit more methodical and just changing one variable at a time is the most efficient way to figure out what I'm trying to figure out. So when you apply the scientific method to answering a question, the kind of thing you get back is a model, which is basically a list of those fundamental rules that we think might be at play in a particular system. And then that model is supported by a bunch of explanations that show how that model actually connects to phenomenon we observe. So we might explain several phenomena given the same fundamental rules and say, look, because I can explain so many different things with the same fundamental rules, this is a good set of fundamental rules to believe in. But the other thing we expect is that there is a lot of evidence that supports that those rules are actually there. It's not good enough to just say, I've took a bunch of data and fit a model to it. We then want to see that that model was tested and that we tried to break it and couldn't. Because if we come up with a bunch of data through experiments and observation, it's, like I said, pretty easy for us. We're creative creatures. We can come up with something that'll fit that data. It's not really that valuable until we also show that it predicted things we didn't already know about. And of course, it also is good if it has competed against other models and it's the one that is the best out of many models. So that's my overview of how I'll be thinking about science for the rest of this video. So now let's try to treat mathematics in a similar way by understanding how it relates to emergent behaviors and what its abilities and limits are and all those kinds of things. Generally, the mathematical mode comes into play when we already have some building blocks, or as they're called in math, some axioms that we want to consider. And we also have some emergent behavior or some emergent structure or property that we believe is correlated to that set of building blocks. We could use a scientific method to support the claim that that particular emergent thing comes from these particular building blocks. But the mathematical mode has a different approach, which is to say, instead of supporting this connection by evidence, why don't we try to make a proof? A proof can give us a much stronger level of confidence than any amount of evidence can, that these building blocks can always be counted on to result in this particular emergent behavior. And that's what the mathematical method is all about. It's the tools of how to construct those proofs, which give us very high confidence. There's, of course, other parts of mathematics. A common thing that you will notice when you look at the early education of mathematics is that you don't do a lot of proofs at all. You get taught how to do number crunching. You learn things like long division, and a little bit later on, if you take like an elementary calculus course, you might learn how to take a derivative of a polynomial or something. And these are actually all algorithms that are being taught, not the proofing methodology. But algorithms are usually sort of supported by a bunch of proofing work that has already happened, and it's more like a mini proof in a small context, where a lot of the larger proofing work has already happened, and the algorithm is just carrying out the final steps of a proof for a small local problem. There's a lot more I could say about how algorithms and proofs are related to each other, but I do think they are distinct things, and I don't want to take this video too far in that direction, so I'm going to pause that topic. So it is my view that it's primarily useful to think of mathematics as concerned with creating proofs and not so much as concerned with creating and executing algorithms like long division. But I can see how it's kind of a little bit of a definitional issue, so I'm not going to try to argue that that's the right way to see it. However, I do think it's useful to be able to label these things differently, because creating proofs is a different kind of problem-solving mode from creating algorithms. And for the purposes of this video, I'm going to use the mathematical mode of problem-solving to refer specifically to the kind of problem-solving where you're creating proofs to connect axioms or basic rules or whatever to specific emergent properties and nothing else. What we ultimately get out of doing math over time is that we get this map of sort of deductive reasoning. We know that lots of things are similar. We can say that these axioms and those axioms are equivalent. This particular set of axioms leads to this set of results. If you're trying to find something with a particular set of results, you can look through the library of math and see what kind of axioms have been found that lead to those results. There's all kinds of useful ways to use this map once it's been created. And of course, it's entirely abstract too, which has the benefit that it can be applied to many different problems. If you're doing science, for instance, and you find a system that has certain behaviors, you don't have to go and ask for new math. If you've already got a mathematical theory that behaves in the same way as the system you're studying, you can just use that math exactly as it is. So that abstraction is a strength of the mathematical system, and it's also a requirement, because proofs are only possible if we start with abstract ideas. In order to get a proof, we need to know how the building blocks work in an exact fashion. So we can't have building blocks that we don't understand, and the only way to fully understand our building blocks is to define them ourselves, which means we're making them up. They're not a part of the real world. This does, of course, mean that the limitation of mathematics is it can never make a claim about the real world. We can never use math to prove something about the universe we inhabit. We can only make a proof if we start from a hypothetical abstract idea and end in a hypothetical abstract idea and never leave the world of abstract ideas. So that is a huge limitation to the methodology. It has to operate abstractly, but that's also its strength. Now let's take a look at engineering through the same framework we've been using. In engineering, the problem starts off with things we already have, resources that are available to us now, the knowledge we have about how those resources interact and operate, and some values, something we either need or want more of in the world that we want to achieve. And the goal of the engineer is to sort of exploit the possibility for emergent behaviors to get more of what we want in the world by arranging our resources in an appropriate way to get that emergent behavior. So the methodologies of engineering are just our best ways of solving those kinds of problems. And I think there are two main principles that are common in almost every field of engineering that I want to highlight for this video. The first principle is that of relying on existing knowledge. And the reason this is a principle is that novelty is kind of risky. When your goal is to create a really strong solution to an important problem, you want to know the properties of the solution you come up with. You want to know how long you can expect it to last, how well you expect it to operate, how much it's going to cost to implement, all that kind of stuff. If you're trying lots of new stuff, then it's really hard to really predict those kinds of things. So a big part of solving an important problem well is sticking within well-known available solutions to the problems you're facing. Now, that might seem strange. How are you ever going to design a solution to a new problem if you always stick within what you know? One way is to just think of it as you're making small adaptations, the smallest possible adaptation to a known solution over and over again. But another way to think about it is that when you want to come up with very novel new stuff, that's just not the engineering mode. You can use the scientific mode or the mathematical mode to explore new possibilities, but the engineering mode is what you do when it's time to have a really strong solution to a problem that you've decided is important to solve. And when you switch to that mode, the wisdom that we pass on as engineers to other engineers is don't try to create a whole new solution from scratch when you could reuse a lot of things that already work. The second principle to take away from engineering is that when you are reaching for values, there's sort of trade-offs and balancing that has to happen between those values. Often it's pretty easy to identify a value that a lot of people will share, for instance, keeping costs low or keeping lifespan of a product high, but you can't easily have both of them. And so whatever you're trying to do, it's useful to know which values you're shooting for in your particular project that you're implementing, right? If you aren't clear on how your values are balanced or what range of those values are appropriate, then you're not quite ready to start the engineering method, because the engineering method doesn't give us any way of answering how we should balance our values. It expects us to have that nailed down ahead of time. This is sometimes referred to as requirement gathering, but you could also just think of it as the prerequisite before an engineering mode can start. You have to have some clarity on what the values you're reaching for actually are going to be. So when the engineering method is being applied, the result is that we have new technologies, which includes things like objects and infrastructures and systems that have properties that weren't there in the building blocks that were used to assemble these new technologies. And it also has the property that these new technologies have capabilities and limitations that are well understood to us. They're not totally mysterious and we have no idea what it is we've created. Hopefully, if the engineering methodology is being applied rigorously and thoroughly, we also understand the new properties this thing that we've created have. It's often important to understand the properties of the newly created technology because those could then become building blocks and yet another layer of emergence exploitation for another engineer, right? For example, if you're going to create an airplane, it's useful to know the properties of the fuel that some chemical engineer is creating. If you don't know what properties it has, you can't really engineer with it. So not only are we passing on the new technologies themselves, but also understanding of what those new technologies are capable of and what their limits are is an important part of the process. So I just presented those three different fields as if they are completely different modes, which are totally separate skills that can be developed. But I think, in fact, they actually feed on each other, and you can't do any of them without learning how to do all of them. And the reason for that is that whenever you're solving a problem in one of those modes, you have to break those problems down into subproblems. And often when you break one of these problems down into subproblems, the new subproblems actually need to be solved using a different mode. The fact that that's the case, I think, is easiest to point out by example. So for my first example, I'm going to take a mathematics problem. Imagine we're going to take a circle and we're going to divide it into n points. We could call this the circle division problem. And there's no rule about where we're going to place the points, but we're going to just place n points around the circle, and then we're going to ask how many regions does this divide the circle into. Now, if we start observing this, when we divide a circle into evenly spaced points, for example, and we see that the first circle gets divided into 2 points, and then the next one gets divided into 4 areas, and so on, we might build up this intuition after we've seen the first few examples that what's going to happen is that at every step we are doubling the circle, and we might write down the formula that the number of regions in a divided circle with n points is 2 to the n. But what we've actually done so far is not a mathematical mode. What we've done is a scientific mode. We've made a few observations, we've formed a hypothesis or a model of how we think this works, and we've said, hey, it's not this big complicated situation, it's actually this more simple set of rules describe what's happening here. And that's the scientific mode that we used. But we have to now, to finish the scientific mode, gather more information. And the way we do that is by applying a few more circles and seeing if it continues to hold. Maybe we could try up to 100 points. And very quickly we'll find out that at 5 points, our formula stops holding. Now at that point, we could say we're done, we don't see a pattern, or we could keep digging until we find a pattern. But once we do find a pattern, sooner or later we want to switch back to the mathematical mode and prove that that pattern in fact holds. I'm not going to do that here, but there is a video by 3 Blue 1 Brown that I recommend checking out that shows the proof that a particular formula does hold for describing this pattern. Mathematicians actually do this a lot. They use a scientific mode to find a pattern and see if it looks like it holds, and then they later try to come up with proofs for those patterns. And they call these things conjectures. If you've ever heard of a conjecture, it's the thing where we think that something is true, but we haven't yet found the proof of it. So another example to take a look at from the scientific field is the recent development of detecting gravitational waves. So making a new observation, collecting new data, that's something that the scientific mode compels us to do. It's the scientific mode that says we need to gather information and observations about the real world. So it's initially motivated by that mode, but the primary problem in detecting gravitational waves is an engineering problem, right? How do you build a tool that can do this? The theory is that we could detect gravitational waves if we could detect very subtle shifts in the geometry of space-time, but in order to actually do that, what we end up having to build is two lasers intersecting at 90 degrees, traveling over 2.5 miles through a vacuum. And setting up that structure is largely an engineering problem. And I think this is a pretty common pattern too. Scientists often have to switch to engineering mode in order to create new devices which will allow them to create observations and measurements. Or they have to switch to engineering mode in order to design and control aspects of the experiments they want to run. So just to round it out, we could also imagine how this sort of thing arises in engineering. So early on in the process of constructing a bridge, for instance, you're going to want to have a design for that bridge and justify that that design is worth implementing. And the way that justification will actually be done is through a mathematical approach. You'll say something like, all of these materials are understood to have these properties and they're understood to interact this way. If all of that knowledge we have about what these materials are like and how they interact is correct, then these things will proceed to happen. And so what you have is kind of a proof. Now, it's not a proof that connects some fundamentally important definitions to some theorems like in the pure mathematics sense, but it is sort of a proof that if these understandings of the building blocks hold and this result we're trying to get does in fact follow from it, then this is a good design, right? It has the same structure of a proof, even though it's scoped to a very particular project rather than being a highly reusable proof. And on the flip side, once the bridge is built, you're going to switch to taking some measurements and testing that bridge to make sure it really does do what you think it does before you tell people it's safe to drive across it, right? That's another demand of the engineering method, is to test it after the fact using a more scientific mode. So the point here is that none of these are isolated skills. In order to be great at one of them, you also have to be able to do some amount of the other ones. Whatever you're trying to achieve might require less rigorous application of the other methodologies in your subproblems, but you want to be able to do some amount of science, engineering, and mathematics in order to do any of the others. Okay, now we're ready to turn back to programming and try to place it among these fields. I think the primary problem that the methodology of programming is concerned with is the design and expression of algorithms. I think this is a distinct methodology from mathematics and engineering, and I also think that while there are a lot of other activities programmers do besides designing and expressing algorithms, all those other activities fit nicely into those other domains we've already talked about. The only thing we need to do is acknowledge that as programmers we have subproblems that are mathematical, scientific, and engineering subproblems, and then we will be able to see that the primary focus of our discipline is the design and expression of algorithms, and that we spend our day-to-day on a lot of other things because that's how all of these fields work. So first of all, let's talk about how programming is a separate methodology from mathematics. Historically, the design and expression of algorithms has been the job of mathematicians. That's largely because we didn't have computers, so the only way to execute an algorithm was to do it on paper using arithmetic and data tables and things like that. And so to carry out an algorithm required some amount of mathematical training and education. For example, the Newton-Raphson method was invented before a computer was invented to do the Newton-Raphson method, so the only people who could be expected to do the Newton-Raphson method were people who knew how to take a derivative. Therefore, it made a lot of sense for mathematicians to be the ones designing and expressing algorithms. We could also take a minute to look at how programming might fit in under the umbrella of engineering. I think they do have some similarities. So if we look at their emergence diagrams, they're both about taking building blocks that are well understood and then arranging them to exploit emergent behavior and get things we want, right? They have that in common. But I don't think that makes them the same discipline. I think engineering has a much stronger relationship with its scientific models as it is figuring out how it's going to exploit emergence, whereas the programming methodology tends to rely almost entirely on mathematical justifications. So, for example, an engineer is going to care a lot about scientific models of buoyancy and air pressure at different heights in the construction of an airplane, and use a little bit of mathematics to show that their design should meet the requirements to fly. Whereas a programmer isn't going to really care about the scientific underpinnings of encryption because there are none. It's entirely justified by understanding integers and other abstract concepts and factorization and stuff like that. So while I'm not really that interested in having a philosophical debate about what programming is and if it counts as engineering, I think it is useful to notice that subproblems that involve information processing involve a lot of skills that are quite different than subproblems that involve things like throughput and latency measurements, which are more engineering skill problems, right? They're more problems that demand the engineering mode. So moving forward, I'm just going to take it for granted that these are separate disciplines because it's going to make it easier for me to give some of the advice I want to give. So now I want to try to use all of this sort of framework to pass on some advice about how to become a stronger programmer. I think it's pretty valuable to be able to take a problem and break it up into smaller problems and handle them piece by piece. And in order to do that effectively, we have to deal with the fact that when we break up our problem into subproblems, sometimes we need to switch modes because our subproblems are actually of a different domain or a different mode than the programming mode that we're familiar with. So I'm going to run through some of the ways that the science, mathematics, and engineering modes can show up in day-to-day programming tasks. I'll get started with the engineering mode. The obvious way that the engineering mode comes up is whenever you're looking at performance characteristics of your code. So if you're thinking about speed in terms of latency or throughput, if you're thinking about how much memory you're using, or if you're thinking about the communication bandwidth you can afford to spend, then you're looking at an engineering mode problem. In fact, more generally, anytime your code is already working, but there's something about it that's not good enough, that's a good clue that it's time to think about it with an engineering mode. So other things besides just the resource constraints that might come up are things like, is it too costly to maintain this code? Is it too slow to build? Are you having some kind of endemic reliability problem where no matter how you try to set it up, you can't seem to avoid getting something wrong and having crashes or bugs? In any of those kinds of situations, you might really be looking at an engineering subproblem. And then the way this whole idea works is once you know that you're in the engineering mode, you take a look at the advice that comes from the engineering methodology, because generally applying that approach to problem solving is better suited to this kind of problem. So that's the big idea. Let's take a look at the same sort of thing again in terms of how the mathematical mode shows up for us as programmers. So the first common place where the mathematical mode shows up is after you've designed a new algorithm or you are attempting to design a new algorithm and you want some kind of justification that your algorithm is correct. The mathematical mode can do this by providing the ability to create a proof that your algorithm is correct, which would be quite a strong way to justify it. We might also end up using the mathematical mode in a very similar way to how engineering mode problems have subproblems that are mathematical mode subproblems. So what I mean by that is you could, for instance, upfront figure out if I need to process a certain amount of data and I'm using a particular algorithm on this hardware, how fast can I expect that to go? That's a mathematical mode problem because you're going to kind of create an argument for a particular speed and say, I think this is the speed I should expect. You are going to be using the engineering style of mathematics if you do that, which is not that you're creating a grand theorem, but you are creating sort of a micro theorem that is relevant to your context. Finally, another place where the mathematical method shows up that I think is not as well understood and is still in the beginning of being developed is in things like type theory or category theory. Now, whether or not these are super useful or not to learn, I'm not so sure. But if you are somebody who likes to do a lot of architectural work and thinking about the way to express things in an algorithm, there does seem to me to be a lot of value in understanding design and architecture of software through some of these lenses. And so if you're trying to, for instance, figure out why one design worked out better than another or come up with a design that's going to work better than what you've got, sometimes having some of these theoretical frameworks helps to understand and move towards better designs more quickly. Let's also take a look at how the scientific mode shows up in programming. So the most obvious way that the scientific mode shows up for programmers day to day is when we're debugging. And the reason that that's scientific mode is because it's taking an emergent behavior and trying to go backwards and figure out how the building blocks underneath it led to that emergent behavior, right? So if you have an emergent behavior in your program, that's the goal. But if it's not the one you expect, then you have a bug, right? Usually you put your blocks together in one way and you expect something to come out. If the thing that comes out isn't what you expect, then we call that a bug and we go into debugging mode. So debugging is just the science we do to figure out how the blocks we put together led to the result we're getting rather than the result we thought we were going to get, which usually means finding out that some of the blocks we put together aren't put together the way we thought they were. And therefore, it's science mode. We're taking an emergent behavior and going backwards to figure out what the blocks are actually doing. Another way that the scientific mode comes up for a programmer day to day is when we're doing things like testing and profiling and other measurements of the characteristics of our program. This counts as scientific mode because, again, we're looking at emergent properties of our program that are either too much for us to keep track of or predict up front, or which are the result of mistakes or code that we're not entirely 100% responsible for by ourselves, or any other number of reasons why we can't just predict what's going to happen and we need to have some kind of verification after the fact. And the third way that the scientific mode can come up as a subproblem in programming is when trying to justify an algorithm's correctness. Now, I said earlier we can do that by a proof, but that's not the only way we can do it. We can also do it by doing experiments and testing it a lot. So for example, there's not really any proof that justifies that a machine learning algorithm is a good algorithm, but instead those algorithms are justified by the fact that there's a lot of evidence that they're good algorithms. Because we couldn't really prove it anyways, given the nature of the problem, it's kind of creating a heuristic. There's no such thing as a perfect machine learning algorithm that is provably correct. Instead, the whole idea is that it's a pretty good one that when we put it to test or put it to use in the real world, it gives really good results. And that's something we can only justify by gathering evidence. So the big idea here is if you can identify what kind of subproblem you're facing, you can apply the correct methodology. Of course, you have to actually practice this. Notice what kind of problem you're looking at, and then bring to that problem the methodology that's appropriate. A thing you might find tricky here is you might not be particularly well practiced in methodologies outside of the programming one, right? If you're a programmer, you might be fairly comfortable writing an algorithm, but you might be fairly uncomfortable creating proofs, gathering evidence in a scientifically rigorous way, or engaging in engineering style thinking to solve a problem. If any of these are a weakness for you or intimidating, then that's going to limit the kinds of problems you can approach using an appropriate methodology and therefore limit your ability as a programmer. So the second step to using this framework is once you can identify a problem and go, I should be using this mode, think about it, what it means to actually use that mode effectively and if you can get better at that mode in any way. I think if you put all of that together, there's a lot of growth you can have just by understanding different subproblems and which skills you need to work on to handle those subproblems better. So thanks for bearing with me on all of this. It's a fairly philosophical video, and I know that's not for everybody. If you did get something out of it, I'd appreciate hearing about how it worked out for you, and if you have any additional thoughts. If you disagree with something and want to point me in a better direction, I'd also kind of love to hear that. It's always interesting to me to think about what programming is and how to relate it to other fields and how to fit it into an understanding of the world at large and how to get better at it. Those kinds of topics just fascinate me. So I'm happy to answer any questions too. If there's follow-up videos that are necessary to explain or expand on any of these topics, I'm open to suggestions. And thanks a whole bunch for watching my videos on this channel and watching this one in particular. See everyone around later. Bye-bye.